So, thank you everyone for attending today's seminar. We are very happy to invite Mengjie Zhang from Victoria University of Wellington to talk about evolutionary machine learning, to talk about some research they have done in Evolutionary Computation Research Group. I will have Jill to introduce a bit about Mengjie.
Kia ora koutou, ko Jill Dobby toko inoa. It's my great pleasure to introduce Mengjie Zhang. Meng is a very good friend of mine. He's also a fellow of the Royal Society of New Zealand, a fellow of IEEE, an IEEE distinguished lecturer. He's Professor of Computer Science at Victoria University of Wellington, and also Associate Dean Research and Innovation in the Faculty of Engineering at VUW. His research focuses on evolutionary computing, and that's what he's going to be talking about today. He's published over 600 research papers in peer-reviewed international conferences and journals. So I could go on. Meng has many achievements, but I think you're all here to listen to Meng talk. So, Meng, I welcome you to this seminar series.
Thank you, Jill, and thanks, Kai-Chi, and for your invitation for me to give a talk here, for me to have an opportunity to meet with our friends in Auckland, right? But I'm still a local person and still, in New Zealand, in Wellington, and although close, but we are not allowed to travel to Auckland anymore, and hopefully this situation can be changed a bit later. So today, my talk is about evolutionary machine learning and research applications and challenges. So here is a quick outline and talking about a little bit about machine learning and then evolutionary computation, and then give some specific aspects or examples of evolutionary machine learning. In particular, these days, we can't ignore deep learning. Otherwise, we are not machine learning people. We are not an AI person, right? So, and then some challenges. And at the end, if we have time, would like to discuss a little bit potential collaborations between two of our groups. And firstly, I would like to ask a question, or a question mark here. And many people, and particularly outside AI and machine learning, think actually AI is actually machine learning, and machine learning is deep learning, and deep learning is deep neural networks, and deep neural networks, CNN, right? And convolutional neural networks. So of course, from application point of view, they only use AI or machine learning as a tool to solve their problems. It didn't really matter for them to code what, but probably in the most recent top AI conference like NIPS, ICML, EJCAI, AAAI, and so on and so forth, and probably over 70 or even 80% of the papers are solving problems using CNN or some variant, and so that gives people an impression. And AI and machine learning, they are CNNs, right? And so, of course, for that purpose, and for people like me who are doing evolutionary computation, probably it's not an AI person anymore, right? But anyway, that's the current situation, and people are doing AI research and applications, particularly the application side. They think actually in this way. But from research point of view, clearly, and they are not the same, right? In terms of machine learning, this is a very big area. And Pedro, and here he draws so-called the 5 tribes of machine learning. And, the symbolic AI or machine learning, this is a big chunk. It was very popular and, 1980s. And these days, this re-assume their, by using kind of learning techniques and have a lot of applications. And this dimension, that's, so-called connectionist, mainly based on neural networks. And these days, neural network is very popular because of deep learning, deep neural network. That's a lot, mainly based on gradient descent search, a kind of stochastic gradient descent or backpropagation algorithm, and so on and so forth. Another paradigm, probably that's the evolutionary learning and optimization paradigm. That's somehow I have been doing a lot, and so that's quite a few people in the world are doing that actually. And another paradigm, is that's based on probability-based learning and Bayesian optimization, Gaussian process, and a lot, right? The fifth one is so-called kernel-based method. A typical example would be support vector machines, right? And the constraint optimization, a lot of research on that. All the 5 tribes and form a machine learning, and it's not a single area or a single, like CNN is only machine learning. That's not the case, right? I'm probably mostly in the evolutionary and neural field, and others did a little bit and for probability, a little bit support vector machines. And actually over 20 years ago, I was doing symbolic AI and machine learning, right? Anyway, this is the case. So today we are going to focus on the whole idea of machine learning, but with the focus of evolutionary computation. So what is the EC, evolutionary computation paradigm? That's also, I draw a very simple figure here. You can see the family is also, is not small either actually. So at least, include actually 2 or 3 big categories. The first one, probably evolutionary algorithm. That's probably the one most people think evolutionary computation is. So many people think evolutionary algorithms, they are actually evolutionary computation. But that's actually before the 1990s. If people say that, I think over 99% of people would agree. But these days, probably that's too narrow. From the middle 1990s, I introduced another paradigm called swarm intelligence. They also have a number of techniques. And basically, you might ask me, what's the difference, right, between evolutionary algorithm and swarm intelligence? Why do they both cause evolutionary computation? Is really swarm intelligence evolutionary computation? I think this is, and many people are still debating that. Today, that's not our focus. So basically what we are saying that, basically the evolutionary computation, and in this definition, in this figure, basically that's my own definition, by the way. So that's population-based algorithms based on beam search. And this kind of a group of algorithms we call the evolutionary computation algorithms. So how to split those two? The evolutionary algorithms, probably that's the oldest in the 1950s, 60s. Genetic algorithms, evolutionary strategy, evolutionary programming. Those are 3 oldest paradigms. Actually, they actually were developed independently from different people, different countries. But until the 1980s, they found that actually the representations are different. And the idea, they all follow population. They all follow, beam search. They are actually all follow the human evolution. And so, and Darwinian gene theory and, survival of fittest. So, and of course, in the 1980s, you can say 1992, and John Koza's book made genetic programming popular, but it actually was born in early 1980s, actually. So those are mainly follow human evolution. But how about swarm intelligence? Basically, this is slightly different. The formal definition would be a population-based search and also a kind of beam search, but mimic actually animals' evolution. And something like, on the ground, like the ants or some other animals, or some birds and in the sky, like, and some bird in sky, or the bees, and the pigeon, and different birds on sky, and so that's kind of can fly, right? And also some animals in the water, underwater, and like a fish, right? So that's a kind of thing. And there are a lot of small animals, by the way, the community, and really dislike that. I want to use the term hate, actually. So they say a lot of animals, people don't like that anymore. So you try to improve the existing algorithms. But actually, from representation point of view, evolutionary algorithm and swarm intelligence, the big two categories, also have a major difference. The major difference is that in the population, in the evolutionary algorithms, all those, actually, they are not connected until evaluation or crossover, that kind of reproduction. They do not connect at all, relatively independent. But in the population, all the individual or potential solutions in the population, in swarm intelligence, in fact, they have a natural connection, like using some kind of topology, like our graph, right? So they are, from mathematical representation point of view, they are actually different. And however, and there are also some other algorithms, and you cannot easily put into evolutionary algorithms, or could not put into swarm intelligence either. I put it that's all other, right? So evolutionary algorithms, swarm intelligence, and other. So from that point of view, many of the learning classifier systems, and also evolutionary multi-objective optimization, which is one of the main algorithms, and very popular. Okay, of course, the swarm intelligence mainly particle swarming optimization and anti-colony and optimization, those stuff, right? So I'm not going to discuss those in detail today. We are going to focus on evolutionary machine learning. In terms of this main topic, actually, we also have two views, I have to say. One is the very narrow view, mainly we call it evolutionary learning, okay? That's, some people interpret evolutionary machine learning as evolutionary learning. This is a relatively narrow view. In general, the evolutionary computation, the figure I presented in the previous page, are actually, in general, have two big categories. Evolutionary optimization, they are optimizing some parameters or some solutions, get a particular solution to solve a particular problem, okay? And this is the big category. Actually, this area still dominate actually evolutionary computation community. But in the recent years, actually, since the 1990s, evolutionary learning also became actually a relatively new, but already 30 years, not new anymore, and paradigm also there. Although some of the old EC people still don't think the learning is a part of evolutionary computation. They're still debating. And my view is that let those people debate, and we do make a progress and with our own effort. Anyway, I'm not going to argue with those people. So from that point of view, those people think, evolutionary machine learning, only the evolutionary learning part does not include evolutionary optimization. This is a very narrow view. On the other hand, and also there is a broad view, actually, and myself is in this category. So the narrow view plus any of the EC methods we discuss here, and to solve a particular task in machine learning, and all those, and I call it evolutionary machine learning. Actually, this view, broad view, was reflected into a survey paper and a couple of years ago, and the Journal of Royal Society invited me to write a paper. Basically, originally I said no, but and after inviting 3 times, I can't say no, and we and organize our group of people write different aspects of evolutionary machine learning. That's actually, I will talk most of them today, actually, briefly. The first aspect probably is evolutionary computation for classification and or for feature manipulation. This is probably one of the oldest paradigm or aspects in evolutionary machine learning community. Firstly, used to constructing and to construct a particular classifier, just like we build a decision tree or support vector machines. Okay? And from that point of view, we also have two categories. The first one is using genetic algorithms or PSO, particle swarm optimization. Basically, we already have a kind of classifier or a model, but the task is to optimize the coefficient and of that classifier. Like if we put a linear discrepant analysis classifier, there are some coefficient, or there are some other classifiers, there are some coefficients we need to optimize that. Traditionally, people use statistics, right, to do that. Here they can use genetic algorithms or particle swarm optimization to automatically evolve or learn those the values for coefficients. That's one category. The second category is to use evolutionary learning techniques to automatically learn a model and also the coefficient or the parameter values for the model and simultaneously. And the typical examples would be the use of genetic programming, learning classifier systems, or artificial immune systems. And so far, both categories of evolutionary learning techniques have been used to automatically learn a classifier, and also for the normal classification, and also for classification with unbalanced data, or you can say class imbalance problem, which means that on one class, or the number of instances is very small, on one or more classes, they have more instances, right? This is a hard problem. Another classification problem is that, and in the data set, there are a lot of missing values, and you don't know what happens. That's actually some of them, that's because, you put some sensor to collect some data, but some, you didn't put enough sensor, you didn't collect them. Some of them, they are very risky. For example, in New Zealand, we know the disaster management, like, the volcanoes, the earthquakes, you need to understand, you need to collect the data from the underground. I was told that this is much, much harder than the weather forecasting, right? Merely collect data from, the land or above in the air. So it's not underground. That's much, much harder. We make collaborations with GNS or Meta Service. Those people have very different views on that. So using our evolution computation techniques, that's all actually those have been doing or have achieved some kind of success. Another big area is feature selection and feature construction or feature learning. This is also a very big area. And in the recent year, actually just early this year, we published a book. And so using genetic programming for feature learning, or including feature extraction, feature selection, feature construction, and other kind of feature manipulation automatically for image classification. So in terms of, this is a big area, and this area actually, and Professor Mengjie is leading this area, and she already created international leadership in this area. And in terms of those, and here this in her actually survey paper, and 5 years ago, they have a full description on that. Okay, So this one, in terms of the evolutionary paradigms, and I showed that before, and for evolutionary algorithms, we have seen mainly genetic algorithms applied for feature selection. That's actually very straightforward. The representation is a bit string. And if a particular feature corresponds to a bit of 1, that feature will be selected. If 0 will not be selected. This is very straightforward. And also using GP and genetic programming can automatically select some important features from thousands of features, from thousands or millions of features. And of course, GP can also do feature construction or combination via some specific functions. Okay, but swarm intelligence also very popular using particle swarm optimization and ecology optimization. Another one I didn't write here is differential evolution, and in the most recent 5 years, that catch up. And also, I mentioned the differential evolution here actually, and also many other methods. So the survey paper mentioned a lot. In terms of evaluation method, that's also applied for filter method, wrapper method, or combination of them. The wrapper method meaning that, and the evaluation, during evaluation of the goodness of feature selection mechanism, you wrapped a classifier or a machine learning algorithm. Filter methods, on the other hand, they don't wrap anything. Okay, it's just using simple statistical measures or information gain or fuzzy stuff. And suppose, and this approach would have much better here, like filter approach. Like there are a lot of distant measures, consistent measures. Yeah, a lot. Also, a PAMI paper, actually transactions on pattern analysis and machine intelligence, and also have a big survey paper on this. That's a lot. So basically, in general, the filter approaches, and they are more general, can be applied to different machine learning algorithms for classification, and usually they are actually, because they don't wrap any classifier, the classification accuracy might be a bit low. So the wrapper approaches, on the other hand, is opposite, right? So that's why people using a hybrid approach. So there's another bigger area is using evolutionary learning techniques for regression. Regression, that's also, here, there's a lot of different categories. I categorize them using the 3 categories. The first one is, we have a lot of models. We just use and GAO, PSO, like to do a model selection. We select the one that best perform on particular an application task. This actually called model selection. It's just like a feature selection, but here we read, the baseline is different models, mainly statistical models here. And also here, there's a second category is that we fixed a particular model. How do you fix that? Basically, if you get the data and, if you have some good knowledge in statistics, you can estimate or you can predict or make assumptions on the distributions. If a group of data, a set of data, follow a particular distribution, and then you can, based on that distribution, and choose a particular model. And then the task become a parameter estimation, right? And so to do that, you just using genetic algorithm, PSO, or ABC means an artificial bee colony optimization, that kind of thing to automatically learn the coefficient of that model. So the symbolic regression, on the other hand, given the area, these days, this is a big data era, right? And Geo is an expert in big data. So, the data is very huge, or they actually, even statistical people or people with a statistical background cannot find the correct distribution for their data. So in that case, it's hard to choose a model. But in many cases, a particular data set might follow a multimodal. So in other words, they have different distributions. It's a mixture. In that case, it's hard to manually select a particular model. In that case, if we don't know the distribution, and we call the symbolic regression. In this case, and we want a machine learning algorithm, like in here, it's generative programming, and to automatically learn the model structure and the coefficient automatically or simultaneously. So here is an example. This is like, here, of course, it's a relatively simple one, polynomial one. But sometimes it's much more, or I can't say polynomial, this is cosine there, right? So that's a lot more complex model, and we can learn automatically using Evolutionary computation techniques. To do this, actually, learning classifier systems and artificial mean system can also do that. Another big category is unsupervised learning for clustering, right? Using evolutionary learning techniques for clustering. And here, so far, EC has been used to solve those problems. And firstly, the number of clusters is known in advance. So that's relatively easy. We know that k-mean clustering is a simple example of this kind, but EC can also do that very easily. But sometimes the number of clusters is unknown in advance. This is harder, right? And EC has been used for that purposes. And also, they say evolutionary clustering with very big dimensionality, with thousands of features. This is much harder, and people have been doing that. We also have done quite a number of works in that scenario. And here, this is a little a visualization here. And at the beginning, probably, it's very clear clusters, but the accuracy or the complexity is very low, but the result is very bad. And then we gradually get better and better. Finally, get a very nice clusters. That's kind of stuff. And currently, actually, in this area, and I give you an example to show what is the difference between evolutionary clustering and the normal clustering, right here. Here we use genetic programming to automatically learn and a kind of embeddings and a model. Let's use the model, and I'm trying to avoid this term actually. And for clustering, traditionally, if we want to do clustering, usually we just we have a set of data. We try to put that into different groups. If we have another data, we need to repeat this process because that's unsupervised learning. We don't really have a learning or training process or testing. We don't, just a single process. Here we are saying that if we use genetic programming, we can learn some models and to automatically put the data point into different clusters. And if we have a new set of data, we don't need to learn from the beginning. We apply this model automatically and get the final clustering result. In other words, using GP, genetic programming, we can also, even the clustering, unsupervised learning, we can have the generalization ability. So this is actually a recent best paper award we got from European conference on genetic programming. So this is quite exciting actually. The biggest challenge currently in doing evolutionary clustering is the lack of good benchmark. This is not only evolutionary clustering, also in general, is the benchmarks are much fewer and the number is much fewer than classification, right? Another bigger category using EC techniques, evolutionary learning techniques for computer vision and image analysis that include actually the pre-processing like edge detection, segmentation, and noise cancellation, and so on and so forth. And almost all the evolutionary learning techniques have been applied to that area. And also image feature manipulation, including feature selection and construction automatically, text feature analysis, and also a combination of safety serve features for complex and feature and image analysis, and also applied to image classification and object detection. In other words, we want to detect very small objects of interest from large images, like satellite images or aerial images that also have been doing and also achieved very good result. And wait a moment, I'll give more examples in that when we talk about evolutionary deep learning, okay? And another category is used for automatically scheduling routine combinatorial optimization. And in fact, this is, I would say, this is a traditional optimization techniques rather than rather than machine learning tasks. However, for small scale static problem, yes, that's usually that's the traditional optimization problems. But for large scale, dynamic, uncertain environment, and then the traditional open research or optimization techniques cannot cope with that. And the evolutionary clustering using a hyper-heuristic approaches and can solve that problem. And that's already has been used in the high-value manufacturing or job shop scheduling. And many of the Amazon, IBM, and Huawei, they are doing that kind of thing, okay? And that's a lot. Also, the traditional bean packing in the port, like all kind of ports, Wellington is small, but also have deep water there, and a lot of ports, Otago, and used in those areas. And also recent years in the web surface computation, that closely, to the database or data mining area, web mining, and also in the cloud computing, and the big server resource allocation problem. And clearly they are, many of them, the large clouds, and also dynamic. And when the server is running, and suddenly from time to time, some particular machine broke down, just broken, and you can't assume that's a fixed number. That's dynamic environment. They have been doing a lot. I would like to say, although they called combinatorial optimization problem, if that's dynamic, large scale, uncertain environment, they become a machine learning algorithm. Task become of machine learning task. Okay. And now I turn to another interesting topic, and deep learning, evolutionary deep learning. These days, as I mentioned at the beginning, if we don't talk deep learning, it seems that we are not AI people, right? And so we are out of date, basically. But what is deep learning? Different people have different opinions. This is actually Professor Zhang, and I invited him to come here to visit here in 2018, actually February 2018, and already over 4 years ago, we had a big discussion. And basically, he proposed, I also had a bit of contribution there, but he actually first presented this actually only last year in IJCAI in Macau, actually. Here, basically, this is if we want to call an algorithm, a deep learning algorithm, it needs to meet 3 requirements, okay, or conditions. Firstly, it should be layer by layer processing, okay? And also in each layer, that's, in the middle layers or hidden stuff, this should have feature transformation. That's his term. What I use, not transformation, but, a kind of feature construction. Like take this node example, and it's constructing high-level features from the previous layer that's considered a lower level features, right? And also the model, the algorithm, need to have sufficient complexity. Why? If the model is too simple and is not deep enough, cannot and eat all the big data, training data, otherwise, and it could be a problem, too simple, and you can't eat and the big data. And also that's easily to get actually and overfitting. And sometimes very large model, like a deep learning model, if you have a very small number of examples, that can also be overfitting. But if a small model that's too small, that's also a problem. You sometimes underfitting, right? And of course, this would be very, very tricky to learn, and basically also require a large, computational cost and computational facilities. And when we, in 2016, when AlphaGo was born, they used, and several hundreds CPU servers, and also more hundreds of GPU servers. And GPU, clearly is more expensive. My lab actually, and here my group, we got over 30 GPU servers here and trying to provide for our students, and spend a lot of money, but still not sufficient. Actually, it's not an easy job. But this has some issues, right? And I already mentioned that, and also say sufficient model complexity, many people just count the number of nodes or number of layers. But we know that a node with a linear combination or is only with an addition or subtraction, that would be very different from sigmoid or from a complex function. We know that, but not necessarily symmetrical. That's all those actually very tricky. And also, in many people think deep learning can solve everything, or everything deep learning is better than anything else. That's not the case at all. Particularly, and if you don't really have a large number of instances, don't use deep learning. And that's a waste of your intelligence and also waste of resources. That's not necessary at all. And also, if you really need something, you want to interpret, you want to understand, and you want to explain the process. And if you use very deep, thousands of layers of neural network, you can't do the explanation. And in the legal domain, in the medical domain, that could cause some problems, right? I have to say, and deep learning these days achieved a lot, that's no doubt. But a problem actually is actually majority of the successful deep learning models using neural networks. And that's not a problem. Neural networks, some people like very much. I personally also like it very much. But the problem is that you need manual design. All the deep models are manually designed. Take an AlphaGo example. They have over 40 experts, all with a PhD, right? Or with a doctorate degree, and a group of neural networks experts, and also some people with actually the domain knowledge. And then they discuss a lot, and then they propose a model, and then they fit into very heavy resources and GPU servers and run. If that's not good, and they change the architecture, they change the parameter, rerun again and again, and then when we want to publish papers we need to compare with them, and then we need to beat their results. So this is actually very hard, and only that's why Google is dominates this area, and Google DeepMind, Google Brain in Japan, they all dominate this area, and they have a lot of resources, a lot of experts. And then when you achieve that, they achieve that, they even publish on archives. And then if you want to publish a good paper in the top AI conferences or journals, you need to compare with them. If your results are significantly worse, your paper will be rejected, basically. So this is a problem. And also, they need all the benchmark they designed very big. The data set is very big, like original CIFAR 10 considered good, and now it's too small, CIFAR 100, and then image that, and then Caltech or others, and get bigger and bigger. And so, and then whether you can explain or not doesn't really matter. You publish. So they want a number, actually. And you need to publish your code, need to repeat. So this is a lot, right? The question is, like we are working in a university or sometimes research institute. We don't have the resources like Google or IBM or Amazon they have, right? Can we use our intelligence to build relatively small models? And more actually, let's say, we automatically learn that models. We don't compete with resources with them. We compete with intelligence. So automated design of deep learning models. And now actually, since actually, only basically, in recent years, actually, that's basically, that's all the state of us deep neural networks manually designed, actually. But using EC, and this is a big area. So this comes to an evolutionary deep learning. But before that, I would like to say in this area, in the automated design of deep neural networks, three main streams: evolutionary computation, and reinforcement learning, and Bayesian optimization, basically. And the Bayesian optimization is the most efficient one. And you can see the EJCAI AAAI papers on NIPS a lot on that. But the final results are not very good. EC currently achieves the best results, state-of-art result, and need resources and more resources. But the reinforcement learning need even more resources than evolutionary computation. But the big companies like those, right? So that's the current system for us. And this comes to using EC, evolutionary computation, to automate the design, and we call it evolutionary deep learning. And this one, I categorize that into two, right? One is the neural network base. Some people call it deep neural evolution. There's a lot of successful examples. With a moment, I'll give you one. Another one is non-EC based, like a deep forest learning, deep PCAs, and many of those. And another one is actually just programming based deep learning or evolutionary deep learning, and also many others. And in actually 2018, and Risto from Texas is a big name, and FB fellow, and he proposed or he claimed EC is deep learning. This is clearly very controversial, but I told people in our group, let's not argue against at this stage, because many years ago, I proposed the term evolutionary deep learning in 2013, 2014, and then many people opposed, and then I quit. Until 2015, immediately before AlphaGo, and I really think this should be called evolutionary deep learning. And then in 2016, AlphaGo was born. 2017, I was invited to give a talk in an international conference. And now evolutionary deep learning is a standard term. Actually, I don't know any other person proposed this term earlier than me, but now it's widely used. But because of this experience, I told our group, don't really deny at the beginning. Let's allow it, and flow for a few years, and people, will get better ideas. So this is one of the example using evolutionary computation techniques, basically genetic algorithm, to automatically learn a convolutional neural network for image classification. we use a variable length representation using crossover and mutation operators. I should probably, and given the audience, I should actually and omit those. There's design some special operators to solve the problem and achieve very good results. And although only we did this first piece of work in 2017, but sent to IEEE Transactions on Evolutionary Computation or on neural networks and learning systems. And we changed and revised twice and only published in 2019 and online and 2020, last year, that's on paper version actually. So, but achieved very good results compared with many of the state of art CNNs and get very good results. This is the error rate. This is the number of parameters that's epoch basically doesn't make big sense, but traditional people use that as a criteria. And also I have to say, number of parameter values. And this one, Google Nest, AliceNet, they are very famous. Use 100 million parameters. Can we understand? Of course not, there's no way. And my postdoc claimed that we learn a much smaller networks and use something over 10 times smaller than those, but still 6 million parameters. 6 million, can people understand? I don't believe that, right? But still very large, very much, and the learned model is a black box, which is a problem. Here is on the MNIST data set. You can see that actually only this one, the LDA net is a kind of deep network actually achieve slightly better results than this, by the way. We all know that, and the neural networks are stochastic algorithms, and different time of run using the same architecture, the same parameter, and different runs, different start experiment will get different results. Those people traditionally only report the best. They didn't tell us how many trials they made. To me, this is a kind of cheating. But if you look at all the over 99% of the publications in EJCAI, AAAI, NIPS, ICML, that belong to that category, actually. So I would always say, need to run multiple tests like 30, if not 30, at least 10. You report the best, you report the mean, you do a statistical significance test. But clearly people don't want to do that. So we achieved actually very good results and later on other data sets. Okay. But as I said, a key issue here, and we also, is the explanation, and we don't understand at all. Can we do better? Let's do actually genetic programming approach. And we learn, and I'm not sure whether we can code deep. I myself would not. And only 1, 2, 3, 4, 5, 6, 7, 8 levels, right? But I have to say, in the neural network community, and sometimes deep reinforcement learning community, 3 levels they code deep. I really have a problem, but that's the state of art. So what the people code confuse people. Here there's only 8 layers, but you can see this program can automatically, this is the face and recognition problem, and automatically learn a small region, a local region. Here we set this raw and start from a particular position and coordinator here, 9, 6, and the length is actually 12. Okay. The next one is a circle here. Here, that's the center. This is the, I can't remember, diameters or radius, right? And so on and so forth. Oh, here is a rectangle, right? And here is a row, it's a line again. You can see using genetic programming, we can automatically detect those regions that are considered important. We know for face recognition, the eye region And the node region, we know that they are more important than many other places. They can automatically detect those regions. And then from those regions, they can actually extract features, low-level features from the local regions. And then from those low-level extracted features can combine them together via, you can see this addition, subtraction, or aggregation mean, or some others, and combine them together to construct and high-level features. And then you can have a simple classifier, or the output, if there's negative one class, positive the other class. So two classes, and achieved, actually this one achieved very good result, okay? And also we generalize that. So we say that we can have automatically learn some different layers: input layer, region detection layer, feature extraction, feature construction, and classification layer. That's using that and automated that. And then you can see we can still learn different programs actually achieved a very competitive result. And then we can, more importantly, can explain, can interpret the model we did. And here, that's a little bit more. And those models are used for feature extraction, feature selection, feature construction, and classification. Here, so we only use generative programming to actually learn a set of features, and then using support vector machines, let's do whether this can be reasonable or not. Actually, also achieve very good results. You can see some extracted features are very meaningful, right? And once you can see that on those and compared with many also CNN algorithms achieve very good results. More importantly, the features extracted from generative programming here and are much better and much easier to understand than if you just visualize original features, actually the pixel value or something. Those features actually are very hard. You can see this much clear and lead to the classification. And here, we can even using a perceptron or linear support vector machines to simply solve the problem. And here you can't, right? I think roughly I would like to, stop something and using the evolution deep learning. But what I haven't talked about, we have been doing a lot, is evolutionary transfer learning. This includes domain adaptation, domain generalization, and multitask learning. We haven't talked. We also haven't talked ensemble evolutionary ensemble learning, and also AutoML, automatic machine learning. This is a big topic. Actually, this big topic and generative programming is playing a significant role. And at least 1/3 of publication in this domain actually from here, right? And there are a lot of challenges I would like to say, and although started and in the recent 20 years, but still, and some people, and we did a lot, but in those 5 areas, at least, there's a big challenges. Theoretical foundation. That's still some people claim that, and many of the evolution learning techniques, you can achieve results. So what? But you couldn't have mathematical foundations. And recently, we also did that in the learning theory, in evolutionary machine learning theory, and also, and we call it actually, and we see dimension actually is very hard. Also, in general, evolutionary machine learning still the computational cost is a problem. Scalability and generalization and interpretation. We have achieved the results, but far more actually than, and we are happy. And so we are still not happy. Otherwise, we don't need to do further research, but we need to do a bit more. the major application areas, and we have applied evolutionary techniques, evolutionary machine learning techniques to many of those, and primary industry and manufacturing, energy, and resource allocation in cloud, internet, finance, a lot of things that we have been doing, right? I'm biased, I have to say, and this area, and I believe actually it still have a lot of space. And when actually Professor Zhihua Zhou visited here, and he also made a claim in IJCAI, evolutionary machine learning in the next 5 to 10 years still have a large space and will become a main direction of machine learning. That's why he added, when he was chairing IJCAI and AAAI, he added evolutionary machine learning under the machine learning category, actually. That's something, and now these days we continue. But still, we need to do a lot of research. And finally, and I know timing is an issue, I use 5 minutes and to brief and what our group is doing, and so that later on and we can and make further collaborations. Currently, and the data science and AI, our group has about 20 members, and basically we have 7 postdocs, and those people, they are in the bigger AI, like robotics, signal processing. We don't count, and some kind of the virtual reality, that kind, we don't count them as AI people. But I know it's bigger AI plus, they should be there. Okay, and we also have over 30 PhD students, and you can see there that's on Zoom because COVID. And since last year and this year, students are on Zoom, actually, unfortunately. And also, and I can say this is one of the largest AI machine learning team in New Zealand, and also probably the largest group with evolutionary learning and focus and in the Southern Hemisphere. When we say group, of course, people can put all people together. We are running regular meetings, and just like what you are doing, have seminars, have meetings together, like weekly or fortnightly. I think we have 6 technology themes. We are doing this, and basically those 6 technology themes actually we are doing. And here, the first one is intelligent modeling and statistical learning, and clearly there's a mixture of people from our statistics and also the learning side. That's a mixture, including people using, we just mentioned, genetic programming for symbolic regression, automatically learn model structure and the coefficients simultaneously. And of course, Bayesian learning optimization and Gaussian stuff there. And we have been solving many problems there. The evolutionary and learning and multi-objective learning optimization, of course, so probably this, we also have many people there. And myself, one of my major area is here. And in particular, the multi-objective, this is some kind of unique. If we have a problem, you have multiple conflicting objectives. And you want to find a good solutions. And the evolutionary learning might be, and actually, I would like to claim it's the best method currently in the world actually to process this problem. I'm not saying other methods can't solve the problem, but the population-based mechanism, beam search, have a natural way to do that. And another bigger area would be the image processing, image analysis, text signal processing. This is a big area, and people have been doing that, and particularly in signal processing. And he's a bigger person, Bastien and Klein, and he recently converted, and these days using more machine learning techniques, and develop a lot of manifold learning, unsupervised stuff, and also natural language processing. A lot of things here is the medical images. Another one, of course, and I have to claim, otherwise I will not be claimed or categorized as an AI person, deep learning and transfer learning. And we have been doing a lot. And in particular, the automated design and learning of digital neural networks. And we have actually good skills there and achieved very good results there. And all transfer learning that we have been doing now. That's another area is scheduling combinatorial optimization. I mentioned a bit. This is a bigger area, resource allocation. That's a bigger group on that. And finally, the explainable AI machine learning. And a typical example would be feature selection, bigger dimensionality reduction. That's also a lot of things. Here, this is actually using the deep model, deep neural networks we evolve. We learned deep neural networks, trying to interpret that, explain that. And recently, we developed some methods. Actually, that's actually a very interesting area. Of course, it's not easy to do. I need to suppose here and stop here and would like to, in those areas, and I'm happy to do collaborations with your group, basically. And before COVID, Jill and I trying to do a little bit more, and then suddenly COVID came, and we haven't met for at least for 18 or 20 months actually in person. So this is caused a problem anyway. And would like to thank Jill and the group and Katerina, and he couldn't be here, and for invitation for me to share my work with your group. And as I said, I'm really look forward to making collaboration with your team. And of course, the work was done not by my own. That's a large group of people, and we thank and all those people acknowledge their work. Thank you very much. Sorry, I made almost actually 57 minutes of presentation, and so I'm happy to answer any questions and also discussions with you. Thank you very much.
Thank you, Mengjie. Thank you for the fantastic talk. So I see there are some discussions in the chat. Michael, do you want to ask questions?
Actually, I prefer you just ask because I'm under the full screen. Probably I just
Michael
stop.
Tai Chi is in control. We can't just ask. One thing that when you were talking about, in particular, this evolutionary programming, right, and evolutionary symbolic regression, I was thrown back because I'm getting older and this stuff happens, to a question I asked at, I think the ILP in 2016, which was like, can these inductive logic programming systems actually, can they be scaled up so that they can give you competitive performance on a problem set like ImageNet? And I think that the answer that you're suggesting is yes, and perhaps in a sense the kind of rules that are induced by an ILP system are like our population, like the population in evolutionary computing. So I think that we should at least explore whether or not there is a specific collaboration on mixed neurosymbolic inductive logic programming, right, where evolutionary computation techniques could be used as part of the theory construction process. So if you would be keen on that, or if I didn't make any sense, if you'd be keen on following up on that, I'd like to schedule a conversation pretty soon.
Thank you very much for your question. This is a very good question, I have to say. And you're talking about symbolic connectionist or symbolic and neural hybrid model. And in fact, when in the 1990s, when I did my PhD, actually, I started from there, actually. And so although I didn't go, but the proposal, initial proposal, came from there. So because clearly the neural side, we said, oh, this is also true for the evolutionary side, right? Basically, it's hard to do the interpretation and, to do the reasoning stuff. But the connection side, that also has the computational and advantages, to automatically learn something, combine them together. What you are saying, if I heard correctly, actually, is that can we just automate that process that would be more hybrid, post-evolutionary and the neural networks or deep or something, and also with some kind of symbolic component there. I think that would be a very interesting direction or topic. Although, in the recent years and like last week, I was also, in the recent 2 or 3 years, I'm also an area chair for IJCAI AAAI. I have a few papers, I have seen a few papers are doing that. And however, I have to say, the results are not as good as, at least I expected. Not very good, but that doesn't stop us from making further collaborations in that direction. But my suggestion, I myself would be very happy to see that. But my suggestion is to choose properly. And if you mentioned image classification, or image analysis is a good area, but not to choose a huge, ImageNet, that kind of data set. And otherwise, you need a lot of computational resources, to be frank, that's GPU resources. Usually we don't have. And I put over 30 now, and now I planned the school asking me using my research grant rather than the university grant to buy 10 more. And I agreed because, last year and this year we didn't travel. We saved some travel money and they asked me to use my own grant. That's fine, but still not sufficient. So I would say you choose an area like, medical, right? Not many instances. And so using the traditional deep neural network cannot achieve very well. And then you also need symbolic knowledge to put together and then got automated design using evolutionary or reinforcement learning to try that could be good. If you choose a very huge data set, I think that could be a problem. That's my suggestion. And I'm willing to discuss more in that direction. Yeah. Or after, via email or talk to you individually. Thanks.
Yeah, I think there might be something we could do in natural language understanding, which is still large data, but it doesn't have to be that large. But yes, let's follow up.
Yeah, and you talk about natural language processing, natural language understanding. I have to say, and in the image analysis area, the automatically learned neural network, let's use neural network example, using EC or reinforcement learning, have consistently and received very good deep learning model and perform actually, outperform manually designed. But in the natural language understanding or natural language processing domain, and because I'm not doing, I don't have much knowledge in natural language, but our group, at least 2 people, they are working on that. However, they haven't achieved better results than the manually designed CNNs. And this is also true internationally. I personally still think the automated design or automated learning of CNN or DNN can outperform or have a good opportunity to outperform actual manually designed. And that have a good potential, but people haven't achieved that result yet. But that means that have a big potential there. Thanks.
Yeah, I think evolutionary design of combinations of transformer blocks is likely to work well, but it's also likely to be extremely expensive, right? But it does seem worth pursuing.
Yeah, that's a good direction, but not sure how. People in this area, that's another interesting area, and I would like to say here, many people think deep learning can do everything or should be applied to every application area. I personally have a strong reservation on that. Some of the hard problems, if they cannot be solved by routine machine learning techniques or not a very deep model, shallow model can solve, my suggestion is that don't use deep, right? And deep has several disadvantages and expensive computational cost, and the model cannot be explained or interpreted. In several areas, that would be a big problem. So I do not recommend people to try deep neural network or deep learning to everything. That's, at least that's my suggestion here.
Yeah, thank you. Any other question? Patrice?
Yes. Do you expect me to ask a question?
I see you're in the panelist, so.
No, yeah. I had a question around with Meng, and he talks about computer vision and what he saw as the major contribution evolutionary methods could do for computer vision compared to the apparent sweep deep learning is doing on the field.
Patrick, that's actually true. And currently, if you look at the evolutionary deep learning domain, or in the deep neural networks, or in that domain, you can see there's a lot of successful examples. And whenever, Google, mainly Google DeepMind and Google Brain, Amazon, they propose a model, and probably 6 months after that, and automatically evolved or learned model started bidding and also performing that. And whenever people get a group of people move that quickly, and mainly for the image classification in that image analysis area. And and of course, I have to say, the main achievement were made by the big companies, and partially, and because they have a lot more hardware resources than the university, like us or the Crown research institute. We can't really compete with them. But we often actually, what we do is, we try to use our intelligence to design some big, good algorithm, develop some big, good algorithm to learn small models, and then to actually also achieve good results those deep models cannot achieve. Actually, I thought, of course, in computer vision image analysis, there are some domains with very large data set. There are some domains like image, the medical images, particularly on New Zealand, like, I started working in the breast cancer and the skin cancer, that's some kind of thing. We have a bigger proportion, of people goes that. But however, when we get the images from the hospital, the number of instances, number of examples is relatively small. What we are trying to do, and we have two different kind of approaches. One is that we borrow similar instances, for example, from hospitals in China, and we build more instances, but clearly we can't rely on them. A second approach is we evolve and we learn models, and also using transfer learning and compensate the small number of examples, having doing that. Yes, and in the evolutionary and computation, evolution learning, we started doing that. Okay, thanks. I know, Patrice, you are also interested and also Michael, the environmental data or the primary industry or different kind of thing. And we also started doing that. And I have to say, the experience that a lot of algorithms that can perform very well on the benchmarks, online benchmarks, even on the CIFAR 10, CIFAR 100 or ImageNet, that's very, very well. On the real world data, sometimes you can't necessarily perform very well. For example, recently we applied that in the Wellington trees. That's segmentation and with land care, and now for the previously developed we tried can do very well. We have to develop a new algorithm to do that. So that's something that's why I don't always trust the so-called the benchmarks. But if you want to publish, you have to compare with them. Otherwise, we are not allowed to. They don't accept our papers. Everything. Yeah, it's a trade-off. Yeah.
Yeah, thanks, Meng. I have a second question, which is stemming also with discussions with students, and there is a peer pressure and you just said it, to push solutions that, at least compared to deep learning, although that might not be useful. You briefly mentioned applications in medical science or in the medical field, and I know from experience that at least with one army, I know they refuse to use any deep learning-based solutions unless they're proven that there's no danger to it. Now, can you give us, for the medical part, and we'll say any kind of study on cancer or whatever, you were discussing skin, do you have any examples where some of these guys actually refuse to take any of the deep learning solutions that would be provided and have accepted some of yours? Do you have a concrete example of that?
And thank you for your question. And in that domain, we have achieved some good results. And I think, some the skin cancer images. One from my PhD student who just finished probably half a year ago, and hopefully she will attend the December graduation, assuming COVID is okay, right? ceremony. And so she used different kind of evolutionary deep learning techniques. Mainly she used genetic programming, deep genetic programming, and used a little bit neural networks, but not CNNs actually. And we are now, it's a bit tricky, and we are still waiting for data set from the industry, and they haven't give us, although they only give a small amount of money, like 200K or something, and asking us to do, and trying to scoping that, but did a little bit, but I haven't produced and deep neural networks and like the breast cancer or actually the skin cancer, but we did produce some good results using genetic programming. If you like, I can send you some of the papers, or I can find the thesis if you like. Yeah.
Thanks. I have a last question, maybe, and I'll shut up after that. I think it's Kaichi's fault. When you ask me to talk, then I don't start, right? Do you have any thoughts about applying your genetic programming algorithms on hyperspectral imaging data, which is becoming a bit more and more, it appears, and there might be some data sets soon, let's say 200 or 300 bands per image. So that's a huge amount of data you can create with very few images, right? Do you have any thoughts on that?
Yes and no, actually. Yes, because recently the Wellington tree image, originally they said, using gray levels, that's, only one band, and then they say RGB, and now they want to use 8 band or stuff and continue to explain. So I have been thinking about that, but have I done any essential work? No, I haven't done much, because the project just started this year. We only put an honors student there. I haven't recruited successfully recruit any PhD student or postdocs doing that yet. So that would be an interesting area. What I'm expecting is that at least using genetic programming, we can do some of segmentation or some species and classification, and to learn some of the features that we can understand. And also people originally didn't think. Like the example originally I showed in the face recognition, I'm expecting that, but I haven't achieved a very good result yet. The owners project made some progress, and I have to say that's far from good, being good currently, yeah.
Thank you, that was great. I'm finished.
Thank you. I have a small question about the last question. If no other questions, so I'm actually currently working with someone from University in New South Wales on machine learning for database. So we're actually using machine learning models to learn the best index structure for, in particular, spatial objects. So I just wonder if genetic programming is able to help in this area, because as I know, so far there aren't much research using evolutionary machine learning in this area. Do you have any thoughts on that?
Sounds catchy, actually. Clearly, the indexing is not my primary area. I know in the that's information retrieval and databases, and that's basically Geo is an expert in that area. So a lot. I'm not sure I understand that area correctly or not. If I answer correctly, genetic programming must not be the first EC algorithm to try. I would say using particle swarm optimization or even differential evolution to try that first, because you want an image, document or some indexing. You want to index something. Probably that's this is not really you are using kind of. My understanding is that you're trying to choose some area that you are interested in to index those target area. So it might be closer to a selection program rather than construction of a whole model. That's probably not quite right, actually. When I said that's probably not. I think probably to answer your question effectively, I guess I need to understand the area better. So currently, I don't claim the indexing this area, and I can understand in full. But I was thinking would start if from the PSO or DE, probably I disclose something, some mysteries or in the EC community. You can see actually, genetic programming can do a lot more than PSO or DE. But if you search the number of papers published in the world, or those citations, PSO domain or DE has probably 10 times and larger than genetic programming. Mainly the particle swarm type PSO and DE, the implementation is actually much, much easier. And although the solution they found are hard to interpret. So basically only probably less than 300 lines, let's put it that way. But the GP code previously and 10,000 lines. So that's something I choose a difficult area, probably that's my mistake. But that's something to start from the easier or easier to do, but also match better and for indexing, I would suggest in that way. But I'm happy to discuss with you later on, otherwise, in more detail if I understand your problem better. Thanks.
Okay. Yeah, thank you very much. I'm happy to talk to you after that. So, do we have any other questions from the audience? No. So I think we can move to the end of the meeting, the seminar. And thanks again for Mengjie's talk. And thank you very much for highlighting the potentials and several directions that can be used, that evolutionary machine learning can be applied. So I think we can keep this conversation going. If you are interested in the area, we can talk to Mengjie. And Jill, do you have anything to add?
No, I'd just like to thank Mong. It is always good to hear, what's happening in an area and also what the future's holding. So thank you very much.
Also, thank you very much for your invitation for me to have opportunity to interact with people, right? So on the COVID period, and very hard to meet in person. I'm expecting that. I'm expecting Jill to come to Wellington, actually. Yeah. Thank you very much. Yeah.
Stop teasing us. We're stuck in Auckland. We cannot come.
Yeah. Yeah, and this is a problem. Hopefully, we will get in there. Yeah.
But we should all get together much more often as well, not only one-on-one.
Yeah, thanks, Michael. Yeah.
We can travel in the boot of the car.
Yeah, some people did that. I'm from Hamilton or drive. Actually, our university has a student. Let's not talk about that. Got the problems, and university have sudden alarms. Actually, that's 5 weeks ago. Actually, we got that. People don't follow the rules.
Cool.
Okay, we'll go next talk.
Sorry.
Okay, thank you. Okay.
Kaichi, what's the next seminar? What's our next seminar?
Yeah, we need to announce that, right?
I think we know already who it is, right?
Let me check. I don't actually remember at this moment.
Is that
but anyway,
yeah. Harrison from Plant and Food, yeah.
Yeah. Right. So see you in a month.
Okay, thank you very much. Okay, bye-bye. Yeah.
See you.
Go home, have dinner. Yeah.